Before I get into this, I need to correct the timing in that headline because being accurate with you matters more than a dramatic hook. This specific signal wasn't detected 5 minutes ago. It was detected by the James Webb Space Telescope starting in 2022 and confirmed through additional observations in 2023. And it remains one of the most genuinely significant chemical detections Webb has ever made from a planet orbiting another star. Here's why it still deserves your attention, even though it isn't breaking news. For the first time in the history of astronomy, scientists caught direct, unambiguous proof that sunlight itself was actively rearranging the chemistry of a distant planet's atmosphere, a process identical in principle to the one that built the ozone layer protecting life here on Earth, happening on a gas giant 700 light-years away. This is the real story of WASP-39b, the specific chemical signal Webb detected in its atmosphere, and why finding it required breaking apart starlight into pieces smaller than any previous telescope had ever managed. If you want accurate space reporting instead of manufactured urgency, subscribe now, because this discovery opened doors that scientists are still walking through today. Let's start with the planet itself, because WASP-39b is a genuinely strange world even before you get into the specific chemistry Webb managed to detect there. It orbits a sun-like star roughly 700 light-years from Earth, and it's classified as a hot Saturn, a gas giant with a mass close to Saturn's own, but with a diameter about a third larger than Jupiter's. An inflated, puffed-up world produced by sitting in an orbit so close to its own star that a complete year on WASP-39b lasts just over 4 Earth days. To put that proximity in perspective, WASP-39b orbits at roughly 1/8 the distance separating our own sun from Mercury, close enough that its atmosphere sits under constant extreme bombardment from its star's high-energy radiation, reaching temperatures around 900 degrees Celsius. It's worth appreciating just how technically demanding this specific detection actually was, because sulfur dioxide wasn't sitting there as an obvious, easy-to-spot feature in Webb's data. The molecule's spectral signature at its original detection wavelength was faint, subtle, and easily could have been dismissed as noise or measurement error by a less capable instrument. Detecting it at all required Webb to break apart the collected starlight into extremely fine wavelength divisions, far more precise than what earlier space telescopes like Hubble or Spitzer were capable of achieving for this kind of exoplanet observation. That precision is exactly what separates Webb's exoplanet science from everything that came before it. Earlier telescopes could sometimes detect the presence of larger, more abundant molecules, like water vapor, in a favorable exoplanet atmosphere. But picking out a comparatively rare trace gas like sulfur dioxide, present in concentrations of only a few parts per million, required a level of spectral resolution and sensitivity that simply didn't exist in any previous space-based observatory. That extreme environment is exactly what made WASP-39b such a valuable target for Webb almost immediately after the telescope became operational. Astronomers study exoplanet atmospheres using a technique called transmission spectroscopy, watching a planet pass directly in front of its host star and analyzing how starlight filters through the thin ring of atmosphere at the planet's edge during that transit. Specific molecules in that atmosphere absorb specific wavelengths of light as it passes through, leaving a kind of chemical fingerprint embedded in the starlight that eventually reaches Webb's instruments, letting scientists work backward to identify exactly which molecules are present. WASP-39b's puffy, inflated atmosphere and its relatively large size compared to its host star made that signal considerably easier to detect than it would be on a smaller, more compact planet, which is exactly why it became one of Webb's very first major exoplanet targets. If a story built on real, peer-reviewed research instead of manufactured urgency is the kind of thing you want more of, drop a like on this video right now. It genuinely helps this content reach more people who'd get value out of it. Webb's first major result from WASP-39b came in August of 2022, when astronomers announced the first unequivocal detection of carbon dioxide in the atmosphere of any planet outside our solar system, a genuinely significant milestone on its own. But buried within that same dataset sat something else, an unusual, unexplained feature in the light that didn't match any of the molecules researchers had already identified. At the time, the team openly acknowledged they'd found what they called a mystery molecule, present in the data but not yet confidently identified. Natalie Batalha, a professor of astronomy and astrophysics at UC Santa Cruz, who led the JWST transiting exoplanet early release science team responsible for these observations, described the situation plainly at the time, noting the team had genuinely interesting features in the data they simply hadn't been able to fully explain yet. That mystery didn't stay unsolved for long. Continued analysis, combined with additional observations, gathered later using a different Webb instrument called the Mid-Infrared Instrument, allowed researchers to identify the source of that unexplained signal. sulfur dioxide, a molecule that doesn't naturally exist in the raw ingredients making up a planet like WSP-39b in any significant quantity. Its presence could only be explained by a specific chemical process called photochemistry, chemical reactions actively triggered and driven by high-energy starlight striking the planet's upper atmosphere, breaking apart existing molecules and allowing the fragments to recombine into entirely new compounds, sulfur dioxide among them. If you found this as fascinating as I did while researching it, drop a comment and let me know. It genuinely helps me figure out what to cover next. It helps to walk through exactly how Earth's own ozone layer forms in the first place, because the parallel to what's happening on WSP-39b is a lot more direct than it might initially sound. High in Earth's stratosphere, ultraviolet radiation from the sun strikes ordinary oxygen molecules, each made of two oxygen atoms bonded together, with enough energy to actually break that bond apart, splitting the molecule into two individual, highly reactive oxygen atoms. Those loose atoms don't stay isolated for long. They quickly collide with other, still intact oxygen molecules nearby, bonding with them to form ozone, a molecule made of 3 oxygen atoms rather than 2, which then absorbs a considerable portion of the sun's most harmful ultraviolet radiation before it ever reaches Earth's surface. That entire sequence, radiation breaking apart one set of molecules and driving the fragments to recombine into something new, is a textbook example of photochemistry, and it's precisely the same underlying mechanism researchers found reshaping WSP-39b's atmosphere, just involving sulfur-based molecules instead of oxygen, and occurring at a scale and intensity shaped by an atmosphere sitting vastly closer to its own much hotter host star than Earth ever sits to our own sun. Here's why that specific finding mattered so much to the researchers involved, beyond simply identifying one additional molecule on a distant planet's checklist. Shangmin Tsai, a researcher at the University of Oxford and lead author of the paper explaining the origin of the sulfur dioxide, described the result in terms that make the significance clear, stating plainly that this was the first time scientists had seen concrete evidence of photochemistry, chemical reactions initiated by energetic starlight, happening on any exoplanet ever studied. That distinction matters enormously because photochemistry isn't simply another category of chemical reaction. It's the exact same basic process responsible for building and maintaining Earth's own protective ozone layer, where high-energy ultraviolet radiation from our sun breaks apart oxygen molecules high in our atmosphere, allowing the fragments to recombine into ozone, a molecule that then shields the surface of our planet from a considerable amount of that same harmful radiation. Finding direct evidence of that same fundamental process actively happening on a planet orbiting an entirely different star gave scientists their first real confirmation that photochemistry isn't a special Earth-specific quirk, but a genuine universal process that reshapes atmospheres wherever the right ingredients and the right starlight happen to meet. The path to actually confirming this discovery required real technical persistence, and it's worth understanding exactly how that process unfolded. The initial hint of sulfur dioxide, detected using Webb's near-infrared instruments, came from a single, relatively small feature in the light spectrum at a specific wavelength, enough to strongly suggest the molecule's presence, but not yet a fully confirmed, independently verified detection on its own. To properly confirm it, a separate research team turned to Webb's mid-infrared instrument, specifically its low-resolution spectrometer, to search for additional sulfur dioxide signatures at entirely different wavelengths than the original detection. That follow-up study, published in the journal Nature, successfully detected sulfur dioxide spectral features at 2 additional wavelengths, 7.7 and 8.5 microns, providing genuinely independent confirmation of the molecule's presence using a different instrument, a different wavelength range, and an entirely separate observation, exactly the kind of rigorous multi-instrument verification real scientific claims require before the broader research community treats them as settled. The cloud detection specifically deserves a bit more attention on its own, because identifying clouds on a planet 700 light-years away, using nothing but starlight passing through its atmosphere, represents its own genuinely impressive technical achievement. Rather than being distributed evenly across the entire planet, the clouds researchers identified in WSP-39b's atmosphere appeared patchy, scattered unevenly across different regions, rather than forming a single uniform layer the way clouds might blanket an entire hemisphere of a planet closer to home. Researchers were able to infer that patchiness by carefully analyzing subtle variations in how starlight was absorbed and scattered at different points during the planet's transit across its star, essentially reconstructing a rough map of atmospheric structure from nothing more than tiny fluctuations in brightness recorded over the course of a single transit. That level of detail, mapping the rough distribution of clouds on a planet nobody has ever seen directly and never will, illustrates just how much information Webb's spectroscopic instruments can actually extract from what amounts to a very faint, very brief dimming of starlight. Once confirmed, WASP-39b's atmosphere turned out to be considerably richer and more complex than researchers had initially expected, and the full picture that eventually emerged went well beyond just sulfur dioxide. Follow-up observations across Webb's full suite of instruments ultimately identified an entire menu of atoms and molecules present in the planet's atmosphere, including sodium, potassium, water vapor, carbon monoxide, and carbon dioxide, alongside the sulfur dioxide itself, in addition to visual evidence of scattered patches of clouds distributed unevenly across the planet's atmosphere. That level of detailed chemical characterization, effectively a complete atmospheric inventory for a single planet orbiting another star, represented something genuinely unprecedented in the field, and it came packaged across a set of 5 separate scientific papers published by the international research collaboration studying the planet. It's worth understanding why researchers found the specific abundance of sulfur relative to hydrogen in WASP-39b's atmosphere so scientifically interesting, beyond just confirming photochemistry was happening at all. Kazumasa Ono, a postdoctoral fellow at UC Santa Cruz who worked on the research, explained that the measured abundance of sulfur relative to hydrogen suggested the planet had likely experienced significant accretion of planetesimals, smaller rocky and icy building blocks left over from the planet's own formation, capable of delivering exactly these kinds of heavier chemical ingredients into the atmosphere over time. In other words, the specific chemical signature Webb detected wasn't just evidence of a process happening right now. It also carried genuine information about how WASP-39b actually formed and evolved over the course of its own history, encoded directly into the composition of gases currently sitting in its atmosphere. Natalie Battaglia spoke directly to why this specific discovery mattered so much for the broader field of exoplanet science going forward, describing the discovery of photochemistry on a hot Jupiter-class planet like WASP-39b as important precisely because it allowed researchers to actually test their existing photochemistry models against real, direct observational data for the first time, opening entirely new avenues of investigation that simply hadn't been accessible before Webb became operational. That's a meaningful distinction worth sitting with. Scientists had built theoretical models predicting that photochemistry should be happening on hot, highly irradiated exoplanets for years before Webb ever launched. WASP-39b gave them their first genuine opportunity to check those predictions directly against real data, rather than relying entirely on theory. There's a broader reason this specific discovery matters for the entire search for potentially habitable worlds beyond our own solar system. Even though WASP-39b itself is a scorching, uninhabitable gas giant with no realistic chance of hosting life. Ozone, and the broader category of photochemically produced molecules it belongs to, is exactly the kind of chemical signature astronomers hope to eventually detect in the atmosphere of a genuinely Earth-like planet. Because on our own world, ozone's presence is directly tied to the existence of abundant atmospheric oxygen, which is itself tied to billions of years of biological activity. Confirming that Webb's instruments are sensitive enough to detect a photochemically produced molecule at all, even one as different from ozone as sulfur dioxide, on a planet as distant and as difficult to observe as WASP-39b, gave researchers genuine confidence that similar photochemical signatures, potentially including ozone itself, could realistically be detected on smaller, rockier, more Earth-like worlds as Webb's observing techniques and available targets continue to improve. In that sense, WASP-39b's sulfur dioxide functioned as a genuine proof of concept, a technical demonstration that the underlying detection method actually works, well before Webb ever attempted the considerably harder task of searching for similar signatures on a small, rocky, potentially habitable planet. It's also worth understanding how this single discovery fits into the much broader arc of Webb's exoplanet research program in the years since, because WASP-39b wasn't a one-off success that never got followed up on. According to NASA's own summary of Webb's impact on exoplanet research, the sulfur dioxide detection on WASP-39b specifically demonstrated the telescope's sensitivity to a genuinely rich diversity of exoplanet chemical compositions and active chemical processes, establishing a template that researchers have since applied to dozens of other exoplanets. Subsequent observations of an entirely different hot Jupiter, called HD 189733b, identified quartz clouds forming in that planet's upper atmosphere, a genuinely bizarre finding involving silicate particles condensing directly out of the planet's scorching hot atmosphere. Other research teams have continued refining exactly how sulfur-based photochemistry behaves across different planets with different temperatures and different host star types, building out a considerably more complete picture of how starlight actively reshapes distant atmospheres than existed before Webb's observations of WASP-39b first opened that door. It's worth understanding why WASP-39b specifically ended up as one of Webb's very first exoplanet targets at all, rather than some other equally interesting world among the thousands of confirmed exoplanets already known at the time of Webb's launch. The telescope's early release science program was specifically designed to demonstrate Webb's full range of scientific capabilities to the broader astronomical community as quickly as possible after launch, and WASP-39b's combination of a large, puffy atmosphere and a favorable orbit made it an unusually efficient target for that purpose, capable of producing a strong, clear signal without requiring the kind of extended, repeated observation time a smaller or more distant planet might need. In effect, WASP-39b served as a proving ground for the entire exoplanet side of Webb's mission, a genuinely useful world in its own right, but also a means of demonstrating exactly what the telescope was capable of before turning its attention towards smaller, more challenging, and ultimately more scientifically significant targets like the rocky planets circling the TRAPPIST-1 system. So, what does all of this actually add up to? The James Webb Space Telescope detected a genuine, confirmed chemical signal from a planet beyond our solar system, sulfur dioxide, embedded in the atmosphere of WASP-39b, a hot Saturn-class gas giant 700 light-years from Earth. That detection, confirmed independently across two different Webb instruments and multiple separate wavelength observations, provided the first direct, concrete evidence that photochemistry, the same fundamental process responsible for building Earth's own protective ozone layer, actively operates on planets orbiting entirely different stars. It wasn't detected 5 minutes ago, and treating it as breaking news would be inaccurate, but the discovery itself remains genuinely significant, a foundational result that continues shaping how astronomers study and interpret exoplanet atmospheres years after it was first confirmed. It's worth taking a moment to sit with what it actually means that this entire chemical analysis, 5 published papers covering sodium, potassium, water, carbon monoxide, carbon dioxide, sulfur dioxide, and patchy clouds, came from watching a single planet cross in front of its star. WASP-39b was never physically visited. No probe has ever been sent anywhere near it, and given its distance of 700 light-years, none ever realistically will be. Every single detail covered in this video was extracted entirely from starlight, filtered briefly through a thin ring of atmosphere during a transit lasting only a few hours, then analyzed down to individual wavelengths with enough precision to identify trace gases present in concentrations of only a few parts per million. That's the genuine scale of what Webb's instruments are actually capable of, turning a brief dimming of distant starlight into a detailed chemical portrait of an entire alien atmosphere, complete with information about the planet's likely formation history embedded directly in its current composition. It's also worth acknowledging the sheer scale of collaboration this discovery actually required, because a result this thorough was never going to come from a single research group working in isolation. The full characterization of WASP-39b's atmosphere, spanning 5 separate scientific papers and covering everything from carbon dioxide to sulfur dioxide to scattered clouds, involved contributions from research institutions across multiple countries, including teams at the Instituto de Astrofísica de Canarias in Spain, the University of Oxford, UC Santa Cruz, and numerous other observatories and universities, coordinating through Webb's early release science framework. That kind of large distributed collaboration reflects how modern exoplanet science actually operates in practice. Dozens of researchers with different specialties, some focused on modeling atmospheric chemistry, others on instrument calibration, others on interpreting cloud structure, all working from the same shared data set to build a single, coherent picture of one distant world's atmosphere. There's a specific reason this particular story is worth revisiting even years after it first happened, rather than only chasing whatever chemical detection is most recent. WASP-39b represents the moment scientists first confirmed that a specific, well-understood Earth process, the kind of atmospheric chemistry protecting every living thing on this planet from harmful radiation, genuinely operates on worlds we'll never visit, orbiting stars we'll never reach. That's not a discovery that expires the way breaking news does. It's a permanent addition to what humanity actually knows about how atmospheres work anywhere in the universe, and it's exactly the kind of foundational result that every subsequent exoplanet atmosphere study, including the search for genuinely habitable worlds, continues to build directly on top of. If stories like this, the accurate version rather than manufactured urgency, are what you come here for, subscribe to this channel and turn on notifications, because Webb's exoplanet research program is still actively building on exactly this kind of foundational discovery, and there's a lot more of this story still worth telling correctly. Thanks for watching, and I'll see you in the next one.